What's up, everybody? Welcome to another video. Hope you're ready to flex those brain muscles. In this video, we're going to practice dividing polynomials using an area model, which is sometimes called the box method. Looks just like this, so if this looks familiar, you're in the right place. And if it doesn't, I hope you still stick around and learn a new method. You might like it better than the traditional polynomial long division. All right, so these are the four examples we're going to go through in this video. The first two have no remainder. The last two do have a remainder to mix it up. The video will be time stamped up, so if you're practicing this, if you kind of already have an idea to do it, pause here, try some of these on your own, skip around, get the help you need. Let's jump right into it quickly with a review of how this area model works. We've practiced in a previous video multiplying polynomials using this area model, and the key idea is that the product of two quantities is equal to the area of a rectangle where one quantity is the length and one is the width. That's the key idea. So we're representing multiplication as the area of a rectangle. Second key idea is that we could break up that rectangle into pieces, and the total area of the rectangle is the sum of all these sub pieces, right? So we're going to have 6 things added together. That's the total area, which is equal to this product. And so we're seeing these like terms, and hopefully where this final answer comes from. We have this minus 2 minus 15. Together, those give us this minus 17. We have 2 and we have 10. Together, that gives us 12. Here we have our biggest term that makes sense. It's the product of the two biggest powered terms in these factors. So we're seeing some different patterns and relationships that are going to become useful, because what we're going to do with division is we're going to think of division as multiplication, which shouldn't be that new of a concept. For example, if I give you 15 divided by 3, one really common way to think about what this is to think about what do I multiply 3 by to get 15. Right? And that answer is 5, which is the quotient. Okay, so we could think of division as multiplication. Instead of thinking of 15 divided by 3, we can think of 3 times what equals 15, and that's the answer. And we could do a similar thing here with polynomials. Instead of thinking of dividing x cubed plus 3x squared plus x minus 2 by x plus 2, we could ask, what could I multiply x plus 2 by to get x cubed plus 3x squared plus x minus 2? So that means x plus 2 is one of my side lengths. I'm trying to find one of the other side lengths, right? I'm trying to find this side length. And what I'm given, x cubed plus 3x squared plus x minus 2, that's the area. That's what all of these boxes need to add up to. So we're going to use those key ideas and try to work backwards and see if we can figure out what that side length is. So first of all, what we saw was a relationship in the last example, which is that top left box was the biggest powered term. That was where the x cubed was, right? And that's always going to be the case. The product of the two highest degree terms in the factors is going to give us the highest degree term in the actual end product. So we can write x cubed here, and now I can think about, well, what needs to go here? And that's what I multiply x by to get x cubed, which is x squared. Okay, and since that little piece is x squared, that means this box has to be 2 times x squared. All right, so now here's how we continue. This is the spot where a lot of kids forget what to do. Remember, we noticed another relationship or pattern, which is that we have our like terms here. Both of these are the x squared terms. Both of these are the x terms. So these like terms are on these diagonals, and they add up to the coefficients of our final product, right? Negative 2 and negative 15 add up to negative 17. That's exactly the pattern we're going to use here. Whatever this box is, we're actually able to find it because we know that these two have to add up to 3x squared, right? And so if they have to add up to 3x squared, then this box has to be x squared, because 2x squared plus x squared is 3x squared. And if this box is x squared, that means this little piece has to be a length of x, because x times x is how we get x squared. And now hopefully you're seeing the pattern. This just repeats. X times 2 is 2x. And now we're back at this step where we need to find this here by looking at what we want to end up with, which is that these need to add up to plus x. We currently have 2x. How do we get x? We just subtract an x, and that's what's going to go here. And that's the pattern. We just repeat this process over and over, right? Since this is minus x, what must be up here? Negative 1, because that's what we multiply x by to get negative x. And then what has to go down here? Negative 2. And now we just need to double check and make sure that the sum of all these pieces equals exactly what we wanted, this, which is the case. X cubed, 3x squared, x minus 2. And what we've just shown using this area model is that what do we multiply x plus 2 by to get this dividend? Well, that's x squared plus x minus 1. X squared plus x minus 1 times x plus 2 equals exactly what we started with. And so that's our final answer here. This is the quotient, x squared plus x minus 1. Awesome. Hopefully that's making some sense. Let's look at our next example here. So for this example, we're thinking about what do we multiply 3x minus 2 by to get 6x cubed plus 29x squared minus 40x plus 12. So 3x minus 2 is one of our side lengths. We're trying to find the other side length, and we know the total area is this polynomial here. And the reason why I leave this open, by the way, is because I don't exactly know how many terms we're going to have. It may seem like it should be the case that this is going to be a quadratic with 3 terms, but sometimes it ends up missing the middle term. Like there's no clear generalization we can make for how many terms by just looking at a division problem. So I just leave it open, and that's totally fine. All right, so let's continue. We're leaving it open. We know that this top left box here, so let me go ahead and mark this up. This top left box has to be 6x cubed. That's always how we start. We're going to fill this in. And now since we know this, we're able to find this piece, which is what do we multiply 3x by to get 6x cubed? Well, we needed 2, because 2 times 3 is 6, and then we need an x squared. And since that piece is 2x squared, I know that this area here is negative 2 times 2x squared, so negative 4x squared. And now this is the tricky piece that kids always forget or mess up. How do I get, or what do I do next, maybe is the better question. What do I even do next? Well, I'm going to find this area. And how do I know what that is? Well, I know that these two areas have to add up to this x squared term, right? 29x squared. So what can I do, add or subtract, to negative 4x squared to get 29x squared? And I believe that's 33x squared. And we could double check our work here. 33 minus 4 is positive 29. We are good to go. And since this piece is 33x squared, now I'm able to find this. And that's the pattern. I'm able to go back here. What do I multiply 3 by to get 33? That's 11. Here I have x. I need x squared, so I need an x here. And now I can multiply this down. Now I know this area has to be negative 22x. And now we're continuing. We're again going back to our polynomial. And we're saying, okay, we know these two have to add up to what? Negative 40x. So I already have negative 22x. I want them to add to negative 40x. So I need minus 18x here. Those now add to negative 40x. And that means I can now find what's here. What do I multiply 3 by to get negative 18? That's negative 6. And there's already an x here, so I don't need to multiply by anything with an x. Boom, it's just negative 6. Amazing. And then negative 6 times negative 2 is positive 12. OMG, we're done. We did it. Awesome. So what we just did was we answered the question, what do we multiply 3x minus 2 by to get this long polynomial here? And that is 2x squared plus 11x minus 6. That is our quotient. That's the answer to this division problem. And we literally have proof of it right here in this box. We can see the area. So we're going to set this up exactly how we've been doing. We're thinking about what do I multiply 2x plus 1 by to get this polynomial here. So this polynomial is the area of the rectangle. 2x plus 1 is a side length. We're trying to find the other side length. So we know this top left piece here has to be 4x cubed. Let's go ahead and label that. I'll separate here. This has to be 4x cubed. And now we can find this term here, which has to be 2 times x squared. 2 times 2 is 4. X squared times x is x cubed. Boom. And now 2x squared times 1, that has to be the area of this piece. 2x squared. So again, what are we doing from here? Now we're able to fill this in. Let's separate it. Do my pink here. Separate it. We're able to fill this in by thinking about what, let's see, how do we make these add together to be 10x squared? That's what we think about. So currently we have 2. How many more do we need? 8. So this has to be 8x squared, which means up here we have to have 4x, positive 4x. And since that's 4x, what's the area of this box? 4x. And now again, we're looking back at our polynomial and thinking, well, we need to get 6x. That's the total area. Right now we have 4x. These two need to add together to be 6x. So I need another 2x here. Let's go and write that in, 2x. Which means this has to be 1. What do I multiply 2x by to get 2x? That's just 1. And 1 times 1 is 1. Awesome. So here's the issue. Here's how we know there's a remainder. Because we just try to find, is there a polynomial we can multiply 2x plus 1 by to get this polynomial up here, right? We want this to be the area. And we found one that got us pretty close, right? Here we have 4x cubed. Here we have 10x squared. Here we have 6x. But here we have plus 1, and we want plus 3. So this is as close as we can get. How much is left over, right? In other words, we can think about what do we have to add or subtract to this area to get what we wanted, and that's plus 2. So there's like this plus 2 left over, or there's this plus 2 we have to add, and so that's the remainder. We have a remainder of positive 2. So how we write our final answer is as this quotient, 2x squared plus 4x plus 1, and then at the end we write plus the remainder over the divisor, right, which is that side length, the thing we are dividing by, 2x plus 1. And so this final thing is our final answer. We have the quotient plus the remainder over the divisor. And let's see if we can make a little bit more sense of why this works. So this first equation directly aligns with what we just showed in our area model. We have this polynomial, and it's equal to the product of these two polynomials, but we need to add 2 to make it exactly equal. That's what we just showed here, right? 2x plus 1 times this quadratic gives us this, which is almost the same, but we need to add 2 to make it exactly the same. So we had this form of the statement here, and one way to think about this is just purely algebraically. How do we get from here to here, which is directly what we wanted to find, which is what is this divided by this? That's what we were asked to find, right? Well, we could get from there to there by dividing both sides by 2x plus 1. When we do that, this entire thing gets divided by 2x plus 1. Here we have 2 terms, so this one cancels out. We're just left with that, and this one just gets divided by 2x plus 1, which is why we're left with that. So purely algebraically is one way to think about it. But the other way is to think about kind of these as 2 different forms. So we can, again, go back to whole numbers when we first learned about this and think about how could we think about 16 divided by 5, what that equals. So 16 divided by 5, that equals something. And how we could think about it again is what can I multiply by 5 to get 16? So question mark here. And if you're a kid, you're probably thinking, well, 3 with a remainder of 1. What does that mean? Well, that means 16 can be written as 5 times 3 with 1 left over, a remainder of 1. This is a true statement. 16 is 5 times 3 plus 1. So how does that show up here? Well, we could write this, right? And when we're really young, this is what we do. We write 3 remainder of 1. But quickly, we like to get out of that and write exactly what it's equal to, which is 3 plus 1, that's the remainder, and it hasn't yet been divided by 5, so we still need to divide it by 5. So we're doing the exact same thing that we did here, which is write the remainder in the numerator and the divisor in the denominator, right? 5 is the divisor, which we can write as 3 and 1/5. So if you have good intuition around writing fractions as mixed numbers, you probably knew that. But these are 2 different forms. When we think about it as multiplication, when we think about it as division, that remainder makes it a little tricky. And we have to sort of think about this relationship between the remainder when we write it as something being added on to multiplication versus when we write it as like the answer to a division problem. Hopefully that makes some sense with what we did here with this remainder. Let's go ahead and jump into the next example here. So here's another thing I love about the area model is that it's a lot easier to deal with these missing terms, I feel like at least. In the long division, you have to notice there's a missing term in the beginning and use a placeholder, and if you don't, you probably need to start over. Here, there's a little more grace, I feel like, but let's try it. Awesome. So we have x plus 3 times what equals x cubed plus 4x squared minus 16. So x cubed has to go here. That's the product of the 2 highest degree terms, and that means this has to be x squared, and so this has to be 3x squared. I'm moving a little bit faster because I think we're probably getting the hang of this at this point in the video. At least I hope we are. Remember, what's the key next step? These 2 have to add together to 4x squared. So I already have 3x squared. What do I need to add? That's another x squared, and that's exactly what's going to go here And so that means what goes up here? What do I multiply x by to get x squared? That's just x. And that means this has to have an area of 3x down here. Now it's the part where we do have to kind of think about the missing term, but it's really not that bad. There's no x term here. Remember, we want to try to make all of these add up to equal this if possible. And so since there's no x term up here, we really need these to cancel out. Since this is 3x, we need this to be negative 3x so that those add up to 0. So there's no x term. If it were like minus 2x, we would need plus 2x. We just take the inverse. We want them to cancel out. So that means this has to be negative 3. And so this has to be negative 9. And now we're down to the constant. So we are done. And so now we need to think about, what do we have here? Well, we have x plus 3 times x squared plus x minus 3 equals this, x cubed plus 4x squared, and then plus 0, which is good, that's what we want, and then minus 9. So it is a little different because this is a minus 16. And now here's how we get the remainder. What do we add or subtract to this area to get exactly what we wanted? Right now we have minus 9, so we need to take away 7 more. Minus 7, and that is the remainder. So here's what we've directly shown from our area model. So this is exactly what our work has shown, which is that when we multiply these two things together, we get x cubed plus 4x squared plus 0 minus 9. So when we subtract 7 from that, we get exactly what we started with here. So this is hopefully becoming somewhat of a familiar form. Here we have our quotient. Here is the remainder. And so again, algebraically, if we divide both sides by x plus 3, on the right-hand side, we get exactly what we want to write as the answer. Or we could just remember that we have a remainder. And so at the end of this, we can add the remainder and divide it by the divisor x plus 3. And this is a great final answer here, unless you're saying, hey, I'd rather write this as positive or write nothing there and change this to a minus. Those are both exactly the same thing. You can write it either way. So this is our final answer to this division problem. And hopefully this video helped you. I really like the area model or box method for division. It's actually, I prefer it over long division. So if you got something out of this, leave any questions below, comment, like the video, and subscribe. Do that stuff to support me and check out my playlist. But most importantly, keep flexing those brain muscles, and I'll see y'all later.